Yeah, the minutes. But I have a clock. 25 minutes.
25 minutes plus 5
minutes.
Okay, so let's continue the morning session. It's a great pleasure to have Michele Del Zotto, who will talk about emergent non-invertible symmetries, bridging UV and IR. Take it away.
Thank you very much. Thank you very much for organizing this fantastic meeting. It's been very exciting to be here and have the opportunity to see so many talks and to talk with many of you, and I'm looking forward to the opportunity of discussing some more later today. Today I will present a work that is a joint work together with my PhD student Daniele Migliorati, my postdoc Shani Nadir Meinet from Uppsala, both are from Uppsala University, and an exceptional collaborator, Kantaro Mori, that doesn't need to be present in the audience. A disclaimer, like the talk, I mean, it's going to be hard to give this talk to this audience because it's so varied. And if it is unclear, it's all about me. Don't blame my collaborators. They understand this far better than I do. So I will do my best to try to convey the message. Emergent non-invertible symmetry, the idea is the usual one. So there is this flow problem in quantum field theories, which is we want to understand relations between ultraviolet physics and infrared physics. And along the RG flow, it can happen that there is an emergent non-invertible symmetry. Emergent non-invertible symmetries are non-invertible, and in particular, therefore, have a higher structure. So they are richer than ordinary symmetries. And from the matching of the higher structure, one might hope to obtain a more robust dictionary between the properties of the IR photons and the ones of the ultraviolet physics involved in the flow. So in this talk, I want to give an example of this effect in the context of 3+1 dimensional adjoint QCD with two adjoint flavors. And I also want to say that shortly after the paper appeared on the archive today, I received some notes. There are some papers about this topic, and by Pace and Pace Zhu, and I'm looking forward to discuss with you some more. Yes, as an introduction, well, we know that four-dimensional gauge theories, relativistic gauge theories, with one form give a way to understand confinement in terms of one form symmetry being unbroken, infrared. I've learned it from this paper by Gaiotto, Kapustin, Seiberg, and Ville, 2014. I was shocked at the time when I saw that talk, Nati. So this is also suggestive of a classification of infrared phases in terms of patterns of breakings of the one-form symmetry, which was ideas that were outlined back in the day, in 2014, in that paper. So now we have seen also in several talks this conference, that there are in 4 dimensions non-invertible symmetries. And the non-invertible symmetries mix zero-form symmetries and one-form symmetries. So since one-form symmetries are involved with confinement in the context of gauge theories, it is natural to think about possible applications of non-invertible symmetries in the context of confining theories. So in this context, a very intriguing scenario to try to probe this idea is that of dynamical abelianization, which is an idea to try to study non-abelian gauge theories in terms of an abelian underlying abelian gauge theory phase, which arises slightly above the confining scale. This idea of dynamical abelianization was proposed by 't Hooft a long time ago. And led to many interesting ideas about the way to understand confinement in 4 dimensions. So in that context, it is known since a couple of years ago that abelian gauge theories can exhibit infinite non-invertible symmetries that have a non-trivial Eiger structure, which we have studied in a project together with Christian and Ifan in the audience and Kantaro. So we want to try dynamical abelianization and to find a gauge theory that we can study exploiting this technique to see whether it has an emergent non-invertible symmetry and whether we can use it to say something interesting about its physics. So a natural candidate gauge theory that has a one-form-center symmetry is SUN adjoint QCD, which is a theory that consists of a Young-Mills field. In this context, it is an SUN Young-Mills field. Is the number of colors, and a collection of Weil fermions in the adjoint representation. So these are Weil fermions, and there are 5 interesting cases corresponding to the number of different copies of the Weil fermions. So if F is 0, one has the Young-Mills theory. If F is 1, the theory is supersymmetric. It has 4 conserved supercharges. It is n equal to 1 super Young-Mills, the minimal supersymmetric gauge theory. If F is equal to 2, 3, 4, and 5, supersymmetry is broken. For 4 and 5, there are Bank-Sachs IR points. And it is conjectured that the theory is gapless. For F equal to 3, I don't know what is the state of the art. So this is a nice class of models to study, to understand confinement in terms of the one-form center symmetry. And in particular, for 0, 1, and 2, it is expected conjecturally that these theories indeed do confine. No? For the case of F equal to 1, this was proved by Seiberg and Witten in 94 in a fantastic paper that kind of changed the history of how we think about supersymmetric field theories. And their idea was to start from a theory that was more supersymmetric, had 8 conserved supercharges, and deform it to flow to the n equal to 1 phase, exploiting precisely the fact that in n equal to 2 you can have a solution of the theory in an abelianized phase. The study proves that n equal to 1 confines. For F equal to 2, there are a lot of papers in the literature that studies it, but a collection of more recent studies is a very good reference to dig into this topic. These are works by Cordova and Dumitrescu of 2018, and works by Docker, Dumitrescu, Nardoni, and Gerkovits. I hope I have pronounced it correctly. There are 3 papers out, and there is a 4th one which is coming, and there are some very nice slides by Emily. She gave a beautiful talk reviewing adjoint QCD at Strings 2022. So in this context, their idea is essentially the same, inspired by this study by Seiberg and Witten. They consider starting from n equal to 2 super Young-Mills and use the abelianized phase there to try to understand something about the dynamics of SUN adjoint QCD, which is non-supersymmetric. So this is the case that we are going to consider. We want to study the case of F equal to 2. And we want to capitalize on these results by this UCLA group about the dynamical abelianization. So let me remind you what is the lore about this theory, and this lore has been confirmed thanks to these more recent studies. So the SUN adjoint QCD is expected to exhibit chiral symmetry breaking by the condensation of the bilinear Weil fermions. And this chiral symmetry breaking will break the SU2 flavor symmetry that rotates the fermions down to a U1. Moreover, this theory has a U1R current, which is the one which is expressed here. And this UR current has an EBJ anomaly, which is non-abelian of non-abelian type. And so only a discrete subgroup survives, a Z4N for NC in general, which is further broken by the gaugino bilinears down to Z4. And in the IR phase, therefore, one expects to find NC disjoint copies of CP1. CP1 arises from the spontaneous breaking of SU2, and the NC degeneracies of the copy comes from the spontaneous breaking of the ZN subgroup of the non-anomalous U1R symmetry. And now, like, the idea is, can we attack this problem? Can we try to study this problem from the perspective of a dynamical abelianization scenario, exploiting the softly broken Schafer-Nameki theory? So this is their philosophy, no? And our remark is that recently Chen and Tanizaki and Sin, more or less simultaneously, pointed out that the CP1 sigma model in 4 dimensions has an infinite non-invertible symmetry. And this infinite non-invertible symmetry is precisely of the same type as the one that was associated to massless quantum electrodynamics. It's exactly the same. And indeed, we expect this matches the non-invertible symmetry of the abelianized theory, and this is something that was remarked. This matching, something that was remarked also by Pace and collaborators. So let me first review a little bit about n equal to 2 super Mills. I know that for people, a component of the audience, this is super obvious. For another component, this is like Arab. so I would say like Arab would sound to me. Not a native speaker. So n equal to 2 super Mills and Schafer-Nameki theory. There is n equal to 2 supersymmetric cousin of adjoint QCD, which is obtained. It has the same content, but an extra adjoint complex scalar. And it is possible to form a Lagrangian combining fields that present 8 supercharges, so twice the minimal amount. And this is incredible. So the class of theories that have this amount of supersymmetry, 8 supercharges in 4 dimensions, are really magical objects. They are related to special Kähler geometries. They are related to hyperkähler geometries on the Higgs branches. They are really incredible mathematical structures. And in particular, they can be solved exactly thanks to this constraint the supersymmetry imposes on the moduli spaces. One finds that there is an effective action parameterizing the Coulomb branch, which is determined by the periods of an auxiliary abelian variety. And this abelian variety has monodromies along the moduli space that are determined crucially by the fact that there are massless particles along the Coulomb branch that causes monodromies in the abelian fibers. So giving a Cartan VEV to the adjoint scalar, Higgs is the gauge group down to a collection of copies of U1. And it is crucial for Schafer-Nameki theory that there are these monodromies. But there are some special points along the Coulomb branch where a maximal collection of mutually local particles becomes simultaneously massless. They are the multimonopole points. And they were remarked shortly after the Schafer-Nameki solution in papers by Argyros Farage, Clem Lercher, Tesain, and Yankelowitz, and then Douglas and Sher. So there are NC-1 mutually local BPS monopole ions that become simultaneously massless, and there are copies of these multi-monopole points that are related by this discrete ZN symmetry that acts on the Coulomb branch. Now, the key idea in the story by Cordova Dumitrescu and then by Docker, Dumitrescu, Nardone, and Gerkovitz, which was inspired by the Schafer-Nameki flow, is to study dynamical abelianization of adjoint QCD, coming up with several possible scenarios that I try to summarize in this picture. So the first arrow here from n equal to 2 down to this red, so this blue bubble contains abelian gauge theories of the appropriate rank. This black arrow here is the Schafer-Witten solution from n equal to 2 super Mills to the n equal to 2 Coulomb branch, and these red dots in the Coulomb branch are the multimonopole points. Now, there is a flow if this M soft is a deformation that breaks n equal to 2 supersymmetry down to 0, giving a mass to this extra adjoint scalar. So we remove it, we integrate it away from the theorem, and this is a deformation that flows to adjoint QCD. Now, there is in the proposal, original proposal by Cordova and Dumitrescu, they conjecture there is a flow that interpolates here and goes close by the abelianized phase of n equal to 2, and then reaches down to the CP1 phase. No? They can explicitly demonstrate that in the context of NC equal to 2, for NC greater than 2, this is done in these slides by Emily, where they explain that there is a cascade that takes you from the multimonopole points down to this collection of CP1s. So this leaves us with various possible scenarios for adjoint QCD in this context. There's a scenario which in the paper we call scenario 1A, where there is a flow and adjoint QCD itself abelianizes, and then it kind of goes nearby this orange arrow representing the flow from the multi-monopole point to CP1. No? So this is one possible scenario. And there is another one in which there is still a flow from adjoint QCD down to this phase, which doesn't involve an abelianization, but is still continuously connected. So there is no phase transition in between. These two scenarios are essentially equivalent from our perspective. And then, of course, there are other options. No? For this theory, there might be other infrared phases, and in our study we don't consider them. We're interested in these two possible scenarios. So, okay. So, what is the matter content at the multi-monopole point? We have an abelian gauge theory. This abelian gauge theory contains a multiplet. This is n equal to 2 supersymmetric. Contains a multiplet that carries the U1 gauge field, and then some hypermultiplets that correspond to the massless monopoles or the massless dions. And here we are using the magnetic coordinates, so the magnetic frame. So the U1 charges here are magnetic charges with respect to the UV. And at the multi-monopole point, there is a U1x symmetry, which is emergent. It is an R symmetry that emerges there. And these are the charges that are dictated by supersymmetries for these multiplets. And on top of that, we have this SU2R symmetry, which is the parent of the SU2R symmetry in the UV. These are the quantum numbers of these multiplets with respect to all of these symmetries. The U1 symmetry crucially has an EBJ anomaly, but this one now is of an abelian kind. So it is precisely of the type that can be saved exploiting the idea of topological defects. Moreover, the Zien one-form symmetry of the ultraviolet theory, the one that measures the color flux, is contained in the U1 diagonal, which is the diagonal product of all the one-form symmetry corresponding to all these copies of Maxwell fields that arise at the multi-monopole point. So there are nc minus 1 of them. No? Now, the non-invertible symmetry at the multi-monopole point is exactly of the same type that we have seen in the talks by Andrea Antinucci and Riccardo Argurio at this conference. So it will be very fast. The idea is that you take a suitable copy of this three-dimensional theory with a one-form symmetry that has the right type of anomaly, and with such theory you can compensate from the anomalous ABJ gauge transformation, and you end up with this collection of defects. So in the paper we work with the Q mod Z representatives of these topological defects. We have seen that there are a more general version of these defects that arise by stacking non-compact TFTs. These choices should carry on. So this is not a choice that will affect our strategy here. It's just a choice that goes. So if they exist for massless QED, they exist also for CP1. And now we have to match them. So what we are interested in is we are interested in matching the quantum numbers of the infrared solitons with the UV ones. No? So we consider, for simplicity, let's start with the case of two colors. And in the case of two colors, this U1x chiral symmetry acts on the fermions, and the fermions will decouple in the flow to CP1 due to the Yukawa couplings. These are Yukawa couplings which are part of the supersymmetric action. And these decoupled fermions, therefore, can introduce some zero modes that couple the U1x symmetry with a solitonic profile for the HI fields. So this effect was discussed already in some very nice papers. One was by Abanov and Wigman in 1999. And another more recent paper was by Sin, Kapustin, and Thorgren in 2020. Where they remarked that if you consider a model where this U1 magnetic subgroup is decoupled, just a global symmetry, along this flow, there is indeed a coupling between a background fields for this U1x symmetry and the soliton number density. No? And the consequence of this coupling is that the skyrmion, in this case, it would be an S3 skyrmion, will carry a U1X charge. No? Now, if one gauges the U1 magnetic, the same argument goes through, only that one replaces the skyrmion with a Hopf soliton, because one replaces the S3 with a CP1. And now, crucially, this U1X corresponds to the quantum numbers encoded in the pi 3 of this CP1. And well, the idea is, okay, but now we know that this U1X is non-invertible, and so if the Hopf soliton number must be non-invertible as well. And this is indeed was remarked by Chen and Tanizaki because of the fact that CP1 has a non-trivial Postnikov tower. So the fact that CP1 has a non-trivial Postnikov tower is an indication that the zero-form symmetry will mix with the one-form symmetry, which means the CP1 is just a consequence of the fact that CP1 is a manifold that has a Keller form. No? So it has a one-form symmetry that comes from that. So this is our matching. And Cordova and Dumitrescu, surprisingly, had anticipated this matching already in 2018. They noticed that improving the current for the U1X with a Chern-Simons density, one indeed obtains precisely the Hopf density for the CP1 model. The only thing that was missing from their study was this idea that you can stack topological field theories to obtain a gauge invariant topological defect, and this is what the non-invertible symmetry does for us in this context. How to generalize for larger n? Well, essentially everything goes through, but the effective action that one gets here gets multiplied by nc-1 because of the fact that there are nc-1 fermions that decouples now, and so this causes a rescaling of the charge. Now, because of this coupling, we find that the Hopf soliton is a fermion when nc is even, and it is a boson when nc is odd. And this indicates that there is a non-trivial theta angle in this sigma model, which was essentially anticipated by Witten in 81. So, like, yes, we are standing on the shoulders of giants. And of course, in the nc equal to 2 case, already noticed by Cordova and Dumitrescu. No? What can we do with this remark that is new? Well, a remark, for instance, is that one can try to find a UV operator that generates the Hopf soliton. And like this can be generated in SQED by an operator that we can identify now. We can write it like this because we can match its charges. We know exactly all the charges that it can have. This one is a good candidate. And now, this also suggests, because of the dynamical abelianization, a candidate to answer a question that was posed long ago by Bolognesi and Schiffman, to try to identify what would be a UV baryon operator for this Hopf soliton. And like the good choice is this one, because this one is a manifestly gauge invariant combination of operators, which is such that it can be rewritten in this way by some Lie group theory. And if you notice, this part here is precisely the one that, upon condensation of the bilinears, will reduce to the one that the abelianized factor in the Coulomb phase. And so it matches the quantum numbers, it matches the fermion parity, and it contains exactly the right number of order of quarks that was requested by Bolognesi and Schiffman in their old paper of about 10 years ago. Yes?
Is there also a WDW term in the sigma model?
Yes.
So the statistics of the Hopfian
this is related to
dependent on NC.
Yes, this is related to the theta angle, the thing that I brought as a theta angle.
Okay.
Yes. Thanks for the question. So yes, this is an example of one such application, and like I'm more or less out of time, so it's a good moment to speak about future prospects. So this was just us scratching the surface of this type of application. Of course, it would be interesting to extend this to other gauge theories without supersymmetries. In particular, we expect that if a theory has an emergent non-invertible symmetry because of its fermionic contact, one can play more or less the same game even without recurring to supersymmetric gauge theories as an avatar for dynamical abelianization. Moreover, this might help improving our understanding of this theory. In particular, there is an effect which is more or less analog to the Kallan-Rubakov catalysis of the proton decay, which is a very, very interesting effect that has received a lot of attention in our community, in the high energy side of our community. Some sort of a Higgs dual of that. There is a vortex catalyzed decays of the Hopf solitons, and we think this type of analysis might be useful to try to tackle this kind of questions about the dynamics of gauge theories. And more broadly, of course, we expect that emergent non-invertible symmetry can be exploited more broadly to formulate dictionaries like the one that we've seen between the UV and the UV charges, UV quantum numbers, and infrared phases that are in particular robust against the RG flow. So this is important. This is an important remark. So you see, this is why it didn't really matter whether we were flowing to an abelianized phase or whether we were going straight to the CP1 phase. Since the CP1 is robust, is attractive, whatever operator becomes irrelevant, dangerously relevant operators along this flow will trigger flows that gets down to the CP1, because that one is stable, is the stable part of the RG flow. So if you are in the basin of attraction of that flow, this study, idea similar to this study will work and will give rise to results that are robust against RG flow. So with this, I think my time is up, and I thank you very much for your attention.
Thanks very much for a nice talk.
This CP1 nonlinear sigma model actually have two versions. One is in the path integral, you allow singularity, another you do not allow singularity. But when you flow from this Fermion model to CP1 nonlinear sigma model, I wonder, do you know which version you actually have, whether you allow or don't allow singularity?
Oh, this is a very nice question. I don't know the answer.
I see. Yeah, it seems that this emergent symmetry from sigma model point of view depend on this feature in some essential way. Yeah.
Thank you.
Since I have the mic, I'll first try to respond, Shogun's.
Thank you. Yes, please.
It's the one without singularities.
The one without singularities?
Yeah, because the SU2 symmetry already exists in the UV. I think you think about it as a symmetry that comes from the lattice, as a model that comes from the lattice. He started in the continuum, so there was an exact SU2, and therefore there are no singularities.
I see, yeah. Usually in condensed matter, we start the non-sigma on lattice, which allows singularity.
I know, you call it non-compact CP1. We discussed it. Now I can ask my question. I understand the non-invertible symmetry you have at the U1 to the N-1 and at the CP1 language. What is it in the UV? I couldn't understand. Maybe you explain it and I missed that point.
There is no such symmetry in the UV. No? It emerges along the abelianization.
Okay, but then if it is an emergent symmetry, how can you use it to get constraints about the IR?
It's a subtle effect, no? Like we don't really constrain the IR using the symmetry. We use it to establish a dictionary between the properties of the solitons and the quantum numbers that we expect for the operators in the UV. No? And this dictionary is crucial that it goes through the abelianized phase. No?
But if all I know about is the UV and the symmetry is not there, how can I have any dictionary between that and the IR? That's
because exploiting tracking the charges, how the charges of the UV theory are represented in the abelian phase. For instance, the color flux, for instance, is a subgroup of the U1 diagonal. No? Out of that, one can conclude that, okay, then the vortices carry color flux. No? And similarly here, this U1x, which is an emergent chiral symmetry from the perspective of this flow, we want to identify it with something that counts some sort of baryon number in the UV. No? But this is essentially motivated by these ideas in the old papers by Witten, no? on chiral symmetry breaking. And so, like, this emergent non-invertible symmetry gives a way of trying to probing this type of idea, no? Giving a way of explicitly identifying the Hopfion, the Hopf soliton quantum number with the U1x, and then with the dictionary between the abelian phase and the UV, tracking it back there. But it's not, yes, thanks.
Okay, I don't see any other questions.
No. No, I missed one small point. So you're saying that the Hopfion corresponds to the baryon. The baryon is charged under U1 baryon. So can you see in the infrared that the soliton is charged under U1 baryon? How do you identify the two? I missed this point.
What do you mean?
Is there a U1 baryon in the ultraviolet, right? A U1 symmetry, a standard U1 symmetry, under which the baryons are charged.
There is a standard U1 symmetry, there is a baryon.
Otherwise, I don't understand why do you talk about baryons?
Yes.
So, but you're matching the baryons with hope soliton in the infrared, is that right?
Yes, well, that's the hope, no? Maybe we can discuss it later.
Okay.
It's a longer, it requires a longer explanation. Yes.
Do you want a question? Yes.
So does this, so in the CP1 you also have the confining strings, but they're not there in the abelianized phase. I guess they're like the topological surfaces, the one-form symmetry. But can you, since you have this non-invertible symmetry which acts non-trivially in the Wilson lines, can you get some constraints by doing this flow like this that you did on the physics of the confining strings on the CP1?
Thank you. It's a very good question. We haven't considered this type of application. It would be very nice to discuss it.
Okay, let's thank the speaker again. And